All right, so as we look through this warm-up really quickly, what part did you guys look at to figure out if it was growth, decay, growth-like, or decay-like? Where should your eyes go to in the equation? The B value, okay? So our B value right here is 7/2, and B is going to fall into the two categories. It's either going to be between 0 and 1 or bigger than 1. So which one will it be for this problem? So you might think that because it's a fraction, right? And we're used to fractions being between 0 and 1. However, this fraction is an improper fraction. So 7/2 is 3.5. So where does that actually fall? More than 1, okay? So the B value is actually bigger than 1. That means this function, along with the fact that the A is positive, will be a growth, okay? So if it's a positive A, that'll narrow it down to growth and decay, because growth-like and decay-like will have negative A values. And then once we look at the B, since the B is bigger than 1, that tells us it's a growth, okay? The shifts are going to come from the H and the K value. That's all there is, Quentin. I'm recording, just so you know. You can say hi to everyone if you want. Quentin says hi, guys. All right, so the shifts, where do they come from? The H and the K value. So what's our H value? 0. So this particular function would have no horizontal shift. And what about the vertical? The -4, so it shifts down 4 units. Domain and range. What's the domain of all exponentials that we talked about yesterday? Good, negative infinity, positive infinity. And the range uses what number? The K, so -4. So it's either going to be -4 to infinity or negative infinity until 4. Okay. Just take a seat, Rayshawn. I'll get you your paper here in a second, hon, okay? So which case will we have? It's going to be -4 to infinity. And you can figure that out by the positive A. Positive A means the graph's going up. So it's going to start at the asymptote and then continue upwards. And the asymptote will be y equals -4 for that one, the K value. So what we're going to do first is actually finish the graph example from yesterday. So if you guys can find that graph paper, I'm going to rewrite the information that we came up with on the board. Finish that, do one more, and then we're going to talk about tables. Yeah, isn't that what that pass is for?
Huh? Yeah.
Why didn't you check in first? Sorry, guys.
I spent lunch with my biology.
Oh, okay. All right. Go check in a study hall. This is going to be a fun video for you guys to watch. All right. Problem from yesterday. We had, if I can find where I put it, this example. Y equals 2 times, I guess I could put it in parentheses, but it doesn't really matter, times 3 to the x minus 1 minus 3. So I believe yesterday we said the A value was 2, the B value was 3, the asymptote was y equals -3. What other information did we get yesterday? The what? It was a growth, okay. So looking at these two, the A and the B, positive A and the B is bigger than 1, meaning it's a growth function. When we go to connect our points, because it's a growth, will that move away or towards the asymptote? You can look at that chart with the 4 graphs, the summary chart from yesterday. Does growth move away or towards? Quentin? Away. So we're going to write that down to think about when we go ahead and plot our points. And then we started to set up our table, right? So our goal is to try to make the exponent 0 and 1. So if I want the exponent to be 0, we sub in a 1, because 1 minus 1 is 0. And if I want the exponent to be 1, we sub in a 2, because 2 minus 1 is 1. So let's actually do that. We're going to show the work and do out our order of operations, because you'll have to be able to do this by hand. So it'll be 2 times 3 to the 1 minus 1 minus 3. That's going to become 2 times 3 to the 0. And what is any base to the 0 power? 1. So it's going to be 2 times 1 minus 3, which is 2 minus 3, and we're going to get a negative 1 value. There's our first point. Okay. Then we can go ahead and sub in 2. So y will equal 2 times 3 to the 2 minus 1 minus 3. We're going to get 2 times 3 to what power? The first, which you don't really need to write that. And we're going to get 6 minus 3, which is 3. Okay. So once you guys figure out your x values, you just sub them in and carefully work through your order of operations. Let's do domain and range, and then we're also going to do the y-intercept for this one, which we might need to use the calculator for. What's the domain? Good, thank you. And what will the range be on this one? Quentin? Good. Starts at k and goes up because it had a positive a value. Let's calculate the y-intercept. In yesterday's example, we didn't have to do this because when we made our table, we subbed in 0 for x, but this time we didn't sub in 0 for x, so to find the y-intercept, we actually have to do that work out. So any intercepts are found by subbing in 0. Y-intercept means we sub in 0 for the x value. So we're going to have y equals 2 times 3 to the 0 minus 1 minus 3. Now we can do this without a calculator. It's going to be messy, but we can still do it. We're going to get 2 times 3 to the negative 1 minus 3. And instead of typing that in the calculator, we can use properties of exponents. Do you guys remember how we get rid of negative exponents? Yeah, move it to the bottom. So this is going to become 2 times 1 over 3 minus 3. 2 times the third is 2/3 minus 3. And then if you subtract that, you can get common denominators if you wanted to. Right now it's 3 over 1. What would you make the second denominator into? A 3 by multiplying them both by 3. And what's 2 minus 9? Negative 7. So your y-intercept is going to be negative 7 over 3. You can change that to a decimal if you wanted to, like if you're working on the calculator. That's going to be negative 2.3 repeating, 2 1/3. Okay. Now you guys go ahead and sketch your y-axis, sketch your x-axis. Instead of doing it on the grid like I normally do, I'm going to do it up here. That way if you're watching the video, you can see what it's going to look like. You're going to first plot your asymptote, which was at negative 3. So at negative 3 on the y-axis, you will draw your dashed horizontal line. And then we're going to plot the 2 points from our table and our y-intercept as well. So we can plot all 3 of those points. The y-intercept was negative 2.3. So on the y-axis, you're going to go down 2 and a little bit more. And then the other points from our table, if I scroll up real quick, we had 1, negative 1, and 2, 3. So positive 1, down 1, and positive 2, positive 3. And way back at the beginning, what did we write next to growth in terms of how we connect them? Away. So it's going to swoop up away from the asymptote, from left to right, arrows on both ends. And then let's go ahead and also finish this with end behavior. So as x goes to the left, and as x goes to the right. All right, so what's happening on the left side of that graph? Where is it approaching? What's it getting closer to? Selena? Negative 3. So on the left side, the graph is approaching the asymptote of negative 3. And what about the right side of the graph? Up to infinity. You got it. Okay. You're talking about the point on the y-axis? Negative 2.3. That was our y-intercept that we got. So when we solved for the y-intercept, we got negative 2.3. Okay, I'm just going to look up really quickly. I know it's a half day, see what time period we're leaving here. And 11 o'clock. Yes, you do, Rayson. All right, so let's do one more quick graph, and then we'll talk about the table stuff. Now, the table stuff is really quick. So the last graph is going to be y equals negative 2/5 to the x minus 2 plus 4. So we're going to work through all those same steps that we just did. First of all, what's our a value in this example? -1. What's our b value? 2/5. So we got a fractional b value here. You still this too, hon. Okay, so 2/5. Will it be growth decay, growth like, decay like? Which one? Decay like. Okay, this time our a is negative. It's going to be below the asymptote, and the b value is between 0 and 1. So negative a and a b value between 0 and 1 is the word I made up, decay like. Okay. Otherwise known as neither. It's not growth or decay. And like decay functions, this will move towards the asymptote when we go to make the graph. What is going to be the equation of the asymptote? Y equals 4. Good. Let's go ahead and make our table. What do we want to make the exponents? What do we need to make the exponent? Okay, so 2 is going to be our first input, because 2 minus 2 will give us 0, and not 1, 3, because 3 minus 2 will give us 1. So let's go through, sub these in, and work through the problem. So y will equal, I'll do it over here, negative, and then we're going to have 2/5 to the 2 minus 2, which is going to become 0. What's anything to the 0 power? 1, and then we multiply it by our negative a. It's going to become -1 plus 4, which is 3. If we sub in positive 3, our exponent is going to be 3 minus 2, which is 1. As long as you pick the correct inputs, you're always going to end up with 0 and 1 in the exponent. So 2/5 of the first power is still what? 2/5. So you're going to get -2/5 plus 4 over 1. I'm going to keep trying to do this all by hand and see without resorting to our calculator. What are we going to multiply the second fraction by? 5. Oops, not 5. That's going to become 20. So you're going to get 18/5. Okay. How many times does 5 go into 18? 3 times. With how many left over? 3/5. Okay, and that's going to end up being 3.6. Okay, 3.6. So let's go ahead and put that in our table. Pretty close to the other one. A lot of times you're going to get 2 points that are very close to each other, and that's okay. Just always keep in mind how it's supposed to look, away from the asymptote or towards the asymptote. And the last point we're going to find is our y-intercept by subbing in what number? 0. So we're going to have negative and then 2/5 to the 0 minus 2. Is that what it was up there? I think. Yeah, 0 minus 2 plus 4. And this might be tricky. Definitely still have to use our properties of negatives. We're going to get negative and then 2/5 to the negative second plus 4. Distribute the negative. So you're going to get 2 to the negative second over 5 to the negative second. How do we get rid of the negatives again? Flip them, move them. Okay, so we have a few steps left here. We're going to have negative, and then you're going to get 5 squared up top, which is 25, over 2 squared on the bottom, which is 4, plus 4 over 1. What will the common denominator be? 4. So multiply this both by 4. So a lot of fraction practice here. This is good fraction practice and exponent practice. And then negative 25 plus 16 is going to be negative 9/4. How many times does 4 go into 9? 2 times with 1/4 left over. So it's negative 2.25 for the y-intercept. Let's go ahead and plot those 3 decimal points. Well, 2 decimal and 1 whole number. Where does the asymptote go? At 4. 1, 2, 3, 4. Okay. Our first point in our table was 2, 3. So plot that. The second point was 3, 3.6. So a little closer to the asymptote. And then what was our y-intercept? Negative 2.25, so negative 2 and a little bit more. And from left to right, for decay-like, we should be moving towards the asymptote. So we're going to be swooping up like this, towards that asymptote. We finish with end behavior. As x goes to the left, and as x goes to the right, so what does the graph do on the left? Goes negative infinity, and on the right, what's it getting closer to? 4. You got it. Okay. Now I know I looked this up before, and I already forgot the answer. See what time we are leaving here today. 11 o'clock. All right, so we got 10 minutes, which will be just enough time to talk about the writing exponentials part. Okay, so this is going to be on a note handout. You already took one, right, Quinn? Okay. So we talked a little bit yesterday that the difference between an exponential function and a linear function is how it grows. So linear functions, they grow by the same amount each time, meaning if you looked at the table, you would be adding the same number in terms of the outputs or subtracting the same number. But exponential functions grow through multiplication because they grow quickly or decay really quickly. So what we're going to do is look for the pattern in the y values of the table. And always make sure that your x's are going up by 1 or else the pattern won't end up being right. So what's happening in the y values each time? Doubling, okay? So each time we are multiplying by 2. Okay, that multiplying by 2 is going to be what's called the growth factor. So we're doubling. In an equation, the growth factor is going to be your b value. Okay, so what it's growing by is the base of the exponent, the growth factor. The initial value comes from your y-intercept. So you're going to look for the coordinate that has an x value of 0, or the ordered pair that has an x value of 0. So in this particular problem, the initial value will be a 1, and that's going to be your a. We're not going to do any table work in which there's an h and a k. So all the ones that we're going to be doing will have an h value of 0 and a k value of 0. So we don't have to worry about those. So the function, if we just set it up into the y equals a times b to the x format, is going to be 1, which I don't have to write, times b to the x. So that would be the equation based on that table. Pattern of growing by a factor of 2. Okay, what about the second one? What's your initial guess? And you can check it on the calculator after, but what would you assume that that's growing by? By 3. Yep. So each time it is multiplying by 3 as you go from left to right. So our growth factor is going to be 3. Can we see the initial value in the table? Can you spot an x-coordinate of 0? No. So we have to actually work our table backwards. And to work backwards, instead of multiplying by 3, what do we have to do? Divide by 3. So if the x value is 1, and I divide 36 by 3, the y value would be 12. And if I go back again for an x value of 0 and divide the 12 by 3, what will we get for a y? 4. So what's the initial value? 4. Therefore, our equation is going to be y equals 4 times 3 to the x. So 2 more of these. So what's happening in number 3? From left to right in the y values. We're dividing by 4. Okay? So each time the y values get divided by 4. To write that as a growth factor for division examples, division in math is always multiplying by the reciprocal. Like when I grade like quizzes and tests, I'm like, stop dividing by fractions. We don't divide by fractions. We can also multiply by the reciprocal instead. So dividing by 4 is the same thing as multiplying by 1/4. Okay, that's our b value, which makes sense. The b value is between 0 and 1, which is why this is a decay function, because the y values are getting smaller. It's decaying, and the b value is a fraction. What will be the initial value? 8, yep. So our equation is y equals 8 times 1/4 to the x. And the last example, what's happening in the outputs there? We're adding 10. Okay. So adding 10 every time is a constant change. Okay. This example right here is not going to be exponential. What type of function do you think it'll be instead? Linear. Yep. So this is a linear function. The initial value is still found the same way, though. What's the initial value? 7. We're not going to call it a growth factor. Instead of calling it a growth factor, for linear functions, it's called your slope or your rate of change. And what's the rate at which this table is changing by? What number? 10. And then we're going to write our equation in y equals mx plus b format because it's linear. So it'll be y equals 10x plus 7. So that's just a little bit of Algebra 1 review. Yes, Quinn? So the first two, as the y's got bigger, they were getting bigger through multiplication, right? We were multiplying by 2, or we were multiplying by 3, whereas this last one is getting bigger through addition. So changes through addition or subtraction is a linear function. It won't be exponential. Okay, this graph would create a line, a constant increase. All right, so that is it. I hope you guys at home are watching this video and taking some notes. And tomorrow we're going to be doing some real world. Okay, so we're going to apply these exponential functions to the real world.